Thank you very much. Welcome to the second morning session. Next speaker is Alfredo Iorio from Charles University from Prague, and he's going to talk about black holes and ultimate building blocks. So please, Alfredo, go ahead. I will let you know after 10 minutes when you have 5 remaining.
Okay, thank you very much, Francisco and Jorge and all the organizers for inviting me. I am partially sad because this is a Zoom meeting. Last year I was in person there in Chile and Argentina. It was much better, but as someone of you said, I think, Olaf, it's a much more populated conference. So I will be way simpler than the beautiful talks I heard before, starting from the talk of Nick this morning. Well, your morning, because essentially we have been venturing since some time on basic questions that you will find in full details in these papers, especially the first two, the one that are in bold, the first two over here. And some of the stuff I will say today, only very briefly, is in this paper that is on the archive a few weeks ago. Couple of weeks ago. Actually, Luca Smaldone will be talking about it in about 1 hour. Okay, so what is it that I'm gonna try to convince you about is the fact that two milestones of what we may call quantum gravity may be in conflict. Okay, and here I took two pictures I identified these two milestones. All right, the first picture is something that wants you, I would like you to think about the baggage time bound. I mean, the fact that the entropy of any system is bounded from above by this number, the entropy of a black hole. Okay, so this is in very bold sense, I mean, said very plainly or brutally. A little bit more precisely, what this bound is telling us is that if you have can you actually see my pointer as well? I am pointing somewhere now.
It's small, but we
Vaguely.
can see.
We can see.
Vaguely.
Yes.
Okay, but so I perhaps describe in words better. Okay, so the one on the left is some matter contained in the sphere. So an area, a regional space-time identified like characterized by a parameter r, and the entropy of everything in there, including the space-time itself, according to the baggage time bound, should be smaller than this number here. And you see on the left there is no reference. There's reference to quantum. There is an h bar. There is c. There is no gravity. And it's only when this stuff becomes a black hole that you reach the bound, and the gravity gets in there. You can get this famous formula by essentially plugging in here the values of the Schwarzschild radius and energy associated to that, and you get this famous bound. We all know that it's holographic, but it's not the holography that is catching our attention here. The fact that it's like a surface, not the volume, but it's the fact that it's a bound, and it must include everything. It must include also this fundamental degrees of freedom that have to talk about the space-time itself. And after evaporation, you go back to a normal situation where the entropy goes below that. Okay, so the other, so this is something that is taken like one of the building blocks of the story. The other building block, another milestone of the story, is the page carve. The page carve tells about the entanglement entropy between a black hole and radiation. So the first point here, where you should see this vague pointer, is about the beginning of the evaporation. The black hole is there. Then you get to a certain maximal entanglement entropy, roughly at the middle of the evaporation, a little bit more at page time, and then you go back to zero. So my thing here, our thing, is that these 2 points are saying that everything goes back to the same. Okay, so you had a situation and you're back to the same situation. All the information is recovered, and what you had before, you have it after. So it's like saying that what's happening here is happening at the black hole. It's also happening when the black hole is gone. But here you have excited the fundamental degrees of freedom, and here you have not. Okay, here I am a little bit getting a bit more technical on. Excuse me, I'm drinking a little bit. on this story. So what Page has constructed there is a bipartite system. So the Hilbert space becomes this tensor product, A and B. This is quite general. Well, apart some technicalities about random states and so on and so forth, he essentially computes the von Neumann entropy between A and B, and he conjectured a formula for this entropy. Actually, it was later proved by a friend of some of us, which is Siddhartha Sen, that the entropy, the formula is actually working. Okay, and then you go and then you plot this thing for the you just keep the thing, the system evolving, and you get this for this beautiful a picture you saw over here that everyone is sort of searching for in the quantum gravity scenario. Actually, last time I was there in that at those latitudes was Maldacena and Verlinde, who were desperately catching up for this formula, for this evolution. Okay, so here I just say what you have to name how to get the black hole evaporation situation. System A is black hole, and system B would be the environment, the radiation, and then you see that this evolution would just fit in this formula. Okay, so how can we try to reconcile this what I claim to be, well, we claim to be a sort of a contradiction, if you like. I mean, the fact that you excite over here fundamental degrees of freedom, and then you go back to standard matter in standard space over here, and from this picture you see no difference between these things. Okay, so we have put forward an idea in this paper of 2017, which we call the quasi-particle picture. Quasi-particle in the sense of condensed matter, because essentially all serious stuff that we do in high energy is coming from there. So we took the same view over here, and we say, well, this fundamental degrees of freedom that we with Bekenstein and somehow with Feynman we call the X level. Okay, these things, these axons have to do everything. They have to make the space and the field. Okay, and it's only when they reorganize themselves, just like it happens in quasi-particles. Here is a picture for the Cooper pairs, okay, that we see them as we see it in our standard low energy description, like matter living on some space background. Okay, but there is always some some field and geometry entanglement. Simply by this, simply should come from the fact that everything is made of the same fundamental X matter. In this picture, then we solved this paradox, if you like. I mean, in this evaporation scenario, you have the same metric G mu nu on both sides, but then the fields become different fields, phi and phi prime, simply because the arrangement may look the same at the level of the space, but the fields in general, we have a different entanglement with the space. So this would be a satisfactory view of reconciliation between the excitation of this fundamental modes, its axons. Excuse me. I'm going. Okay, of these fundamental modes here, this axon here, and the fact that you want to have a page evolution of the thing. Okay, so let's see how this philosophy can get to to some calculational answer to the black hole evaporation. Now I'm going to present to you what we have done last. So this is a paper of last year, 2020, which actually should be something we should have done at the beginning, but we didn't manage in the beginning, so we only managed later. Let's look at the point of view of this fundamental entities, these axons. So the black hole, what I claim is that it's only. Let me repeat just briefly from this. Okay, the page curve here, what I'm claiming is that this page curve only makes sense if you are including all the degrees of freedom, including the degrees of freedom for that should make the space itself. So these fundamental degrees of freedom, the axons. So we should be able to reconstruct an evolution like that entirely in terms of these fundamental objects. And so that's what we tried and somehow succeed to do in that sort of toy model, when we have claimed that the fundamental degrees of freedom are fermions, and here I call A everything that relates to the environment, and B to the black hole. This is the dimension of the Hilbert space. And we start off with everything into the black hole. So see, all the states are here created by this B modes. So these are, we start with 0 n, and you have to end up into n0. How do you so the generic state will look like this formula over here. It looks a little bit complicated, but it's nothing more than a superposition of all possibilities over here. And the beauty of that is that you can introduce operators which look like the entropy operators of thermofield dynamics. Okay, you can introduce one for the environment and one for the black hole. So you see A and B over here. You take averages on this state, which is going to be the von Neumann entropy of the state. Okay, and these are the objects that then you should be able to measure. Okay, so you introduce this entropy operator formalism, and then you go down to the averages, which are something you measure. Okay, we still some way to go from the page construction, because we need to define this number operators, and only after you have averaged over those states psi sigma, you can introduce this N and M. We should remember that this N and M were the dimension of the Hilbert spaces associated to black holes and radiation. So if you do that, okay, then you are able, through this new definition, to identify the Begic entropy, the environment entropy. So you have the three ingredients of the curves that the quantum gravity people all plot in this case, which is the entanglement entropy. Doesn't matter if you take S1 of S2, they have to be the same. And then the black hole in the environment. And the beauty is that this is it. Okay, so the red curve will be the page, the black hole, the Begic will be this one, the black one, and the green one will be the environment. Everything fits. If you like, we can discuss then differences between this a standard thing. So this is now making sense, because this is entirely done in terms of fundamental objects, and we've been able, by the hypothesis, making the hypothesis that the fundamental objects are fermions, we were able to reproduce the page curve. Okay, but this is not
4 minutes.
I know. So matter and space points of view is what we actually have to look for. So what you have to be able to is to find a projecture, a map, where you actually can sort of split the degrees of freedom in there from those making the geometry, the space, and those making the matter. Okay, so after this has happened, the psi itself can be factorized in this way, and you do some hypotheses that say, well, there are different kinds of rearrangements. You can rearrange the degrees of freedom in different ways, so that the final dimension is this one, and the general states as essentially superposition of objects which belong to the geometry part, the space part, and the matter part. Now you just do some technicalities, and at the end of the day, what you have to do, you have to trace away the geometry. We don't see any geometry at our energy, and all you're left with is a density matrix description of the fields. So you go through the standard calculation, the von Neumann entropy. Now in this approach, where you have distinguished geometry and matter and space degrees of freedom, and this is an example for a particular choice of arrangement, very simple, two possibilities only. So you find two different ways, for instance, of making 1500s, which is 30 by 50 or 60 by 25. Okay, this is a very toy model thing, and you allow for 30 quanta. So you have a black hole that started off with a mass equal 29 actually, and ended up with complete evaporation, 0. So you plot that, and beauty, you get something different from 0 at the end. Careful, this is not a page. This is not a page, because this is not entanglement between radiation and black hole. This is entanglement between matter and space. Okay, so what you have to compare are the two end points, the beginning and the end. And the important thing is that at this point you have a non-zero. So this is the relic of the entanglement between fields and matter, and this is somehow something that would okay, my collaborators would resist this word of mine, but I would say it would explain the information paradox somehow. The fact that at the emergent level, you will never end up at the same level where you started. Okay, this now makes much more sense to us. All right, this is only the beginning of the story. The conclusions is that from the Begic bound, and actually I didn't say anything, but ADS-CFT itself insisting on the same degrees of freedom from two different description, a gravity and a field theory description. They imply the existence of the X level. As I said, the name is not our name. This is the name that given by Begic. What I personally use, it was the name of given to Feynman to objects that he defined in the discussion about analogs. analogs of electrostatics, but that's a different story. If you like, we can talk about it later. Okay, and both space and matter have to be made of the same X material. Let me say, if you suppose that the axons are fermions, then you have this beautiful result that you can reproduce some form of the page curve, which is something we didn't do. We were not able to do at the beginning. Indeed, you saw I presented first a 2020 result and then a 2017 result, and but the 2017 result is the one that we should actually be able to measure, in the sense that this is where you see the unavoidable relic between matter and space entanglement. There are a variety of open theoretical problems. One is the dynamical map from this fundamental degrees of freedom to fields and geometry, the Stone-von-Neumann theorem itself, and how you can actually break symmetry in this finite dimensional Hilbert space contest. But on this, Luca will comment. We'll actually have an entire talk later. How to actually introduce a true thermal behavior. I show you some sort of thermofield dynamics operators, but you saw no temperature over there, no fields whatsoever. Okay, and a lot of theoretical open problems on which we are discussing. But I also am very keen on trying to solve, enter quotation marks, this puzzles using, for instance, analog physics or some other form of testable experiments. I mean, real things in the lab. Okay, again, the three papers where the stuff was taken. Okay, in the chronological order, although I talk about it in sort of a reverse order. Here are the people that contributed to this. These three first row are the co-authors. The first person you see here is Martin Scholz, with whom I personally initiated all this business. Unfortunately, Martin died very young in 2019, and he left us. But we're still very much inspired by his beautiful comments and beautiful work. Georgios participated in the discussion at various stages, and Pablo and Paolo are always welcome in all discussions about this, and Pablo will also talk about it later. Let me just close with 1 second, which is an advertisement for a dedicated special issue of Universe on quantum gravity phenomenology. I am chasing Nick Mavromatos since a long while. He says he doesn't want to contribute. I will try to everything to get him in, and everyone else is very welcome to apply. We still have some room. We have some nice people contributing. If you're interested, you can write to me privately at this address. Thank you very much.
Okay, thank you very much, Alfredo. And we have 3 minutes for questions, and already Nick has a question. So Nick, go ahead.
Yes, thank you very much. First of all,
how can you contribute to the issue? It's easy. I mean,
that's a very nice talk. First of all, very interesting ideas. It's not that I don't want, because of the online teaching preparation that we have in UK.
Yeah, but I moved the deadline. I moved the deadline to July 30. So
still that doesn't help. Let me ask the question.
Go ahead.
Approach. So my question is 2 very short questions. One is, what's happening with the information paradox? Can you resolve it completely, or because of this inaccessibility, practically in practical terms, you would still have deviations from quantum mechanics if you have presence of black hole? That's my first question.
I can answer straight away, or you want to do both questions?
It's up to you.
Okay, let's answer. Okay, yeah. So if I want to be very mysterious, I can just tell you that the answer is in this prime over here. You see, the phi prime.
Right.
Well, this is a mysterious sound, but I don't want to be mysterious. The idea is that the fundamental objects, the fundamental accents, should do like this. Okay, that's so right. you have no loss or anything. It's completely unitary. You start off from here at the beginning of the evaporation. You end up at the same point. The point is that we don't have access to the accents.
That's right. So that's what my question is.
In practice, this is more than practice. It's emergence. It's emergent. The only thing we have access to are fields on a background. From that point of view, you never, we could be actually precise and make some calculation of the probability of recovering exactly the same situation as before. I'm sure we get a set of zero measure. Okay, and this is seen, I think, if I if I manage to do some magic with the thing here, I should. How can I actually show this?
And while you're searching, I'm asking my second question, which is
Yeah.
related. Is CPT invariant your construction or not?
It is what?
Is CPT invariant your construction? Do you have
Oh,
a time
oh,
reversal or not?
well, we don't even have time there.
Okay,
we
you
are
don't
in
even
very
have time to
see
ask.
this.
Good.
Can you actually see the transparency here? Or,
Yes, not in full screen, but we can. Yes.
okay, you see the first this thing I showed to you is it ends up very close to zero because we took only two possibilities, only two arrangements. As soon as you take more or arrangements, this is just for I think 5 or bit or 30. Well, I don't know, bit more arrangements. You see that the relic entropy gets bigger and bigger.
Right.
So it is a very interesting calculation to do, and probably we have to do it, is to see that if you take realistic numbers, so you take how many possibility would allow to essentially it's a calculation of microstates associated to macrostates. So if you have many micro arrangement, it will give you the same macro arrangement. How many of them you have? This page thing will be badly violated as soon as you put in very realistic numbers. If you only give two possibilities to very small Hilbert spaces, you immediately have some violation. You put a little bit more of this violation, and you see more and more. I see the formation of the curve. So my personal idea is that if you include the realistic numbers, you have a very sizable violation of the page curve. But you see, we take a sort of a half-away conservative view because we say, look, you want to insist on unitarity. Well, no problems. You insist on unitarities, but then you should describe in a unitary way how the fundamental objects evolve. Those are the fundamental. Those are the guys who have to evolve unitarily. Then the whole question opens whether you can have access to this unitary evolution or not. Okay.
Thank you. Thank you very much.
Can I ask a question?
So we are almost on time. It's a quick question.
Yeah, it's a quick question. The Alfredo, this X object, it cannot be accessed as a matter of principle, or it's a matter of energy. For instance, at the beginning of the universe, there was enough energy that they could be seen, they could be excited, or whatever.
I would say that at the beginning of the universe, you may be even able to see them. I mean, the thing is that this, I mean, the idea is quite simple, and it is actually again from this point of view is Bekenstein idea. This name, the X level, if you see even in this popularizing papers, popularization papers like on Scientific American, it talks about this fundamental level. It's a fundamental. If you say that this is a bound on entropy, it means that you have excited all the degrees of freedom. Now, how do you excite these degrees of freedom? In here, it's done through the black hole. If you have another way of getting the same amount of energy, okay, and distribute it in such a way that you excite everything, then you have it. You have it at the beginning of the universe. You have it there. From what we can see at this scale of energy, the most natural place to see them is at the black holes.